So welcome Carlos Arreche, who will speak on Mahler residues and telescopes for rational functions.
Okay, hello everyone. This is thank you to the organizers for setting up this lovely virtual conference and for inviting me. I'll be discussing joint work with Yi Zhang, who I had the pleasure of working with when he was a postdoc at UT Dallas a few years ago, and I hope that you get to meet him in person at some point. And if you haven't worked with him yet, try to somehow, because he is fearless. So let's see. So before I discuss this notion of Mahler residues and what they're for, I want to begin discussing the basic and very familiar analog that motivates different notions of discrete residues. So suppose I give you a rational function, and let's say that I've already decomposed it into partial fractions. I'm interested in the question of whether f can be written as the derivative of some other rational function, and it's well known from calculus 1 course that f will be well, I'll call for a second rational integrable precisely when all the first order residues vanish. So the question of whether f is the integral of a rational function is in some sense continuous analog of similar questions that can be posed in the context of difference equations, where I have in mind in particular shift different equations where you send x to x plus 1, or q dilation difference equations where q is just some non-zero non-root of unity number. Mahler difference equations are the main topic for us today, and then I'm also interested in similar questions for elliptic difference equations, which I won't define, not even verbally, but if you're curious, please ask at some point. Okay, so let me tell you what these discrete residues are, and I'm going to start discussing in great detail work that is not my work with Yi, but rather the work of Chen and Singer from 2012. Where they developed these two notions of discrete residues in the shift and q different case. And I want to discuss this in detail because you're going to see that there's, as you progress from shift to then q difference to the Mahler difference, things get substantially more complicated at each step. At the very end, I won't be able to write down a formal definition of the Mahler residues for you because it's so complicated, and this is somehow work in progress, but I'll tell you what the eventual formula will be defined in terms of. Okay, this is not complete yet. We're almost there. Okay, so discrete residues in the shift case, what you do is you again decompose your rational function f into partial fractions, and notice here that I've decomposed it in a bit of a funny way. I've gathered together all of the poles of the rational function that differ from each other by integers. Okay, these are all the things that are, if you like, in the same sigma orbit, where sigma is the shift x to x plus 1. And from that decomposition, you then define the discrete residue of f at the orbit alpha. Here I'm collecting in the bracket alpha all of the integer shifts of alpha. And then at each order, you add up all the poles for all the different shifts of alpha at that given order I. That is the discrete residue of f at the orbit alpha of order I. And it turns out that Chen and Singer proved that these discrete residues form a perfect obstruction to the problem of deciding whether f is rational summable. That is, whether f can be written as some rational function g evaluated at x plus 1 minus g of x. This is a discrete analog of an integral somehow. Sorry, I should say it's a discrete analog of a derivative. This difference of the g's, and the way that you show this at the very end, I'll get into some part of this argument in the Mahler case is by trying to subtract from F things that look like sigma of G minus G, like carefully constructed from the things in F, and at the very end you end up with a rational function having no dispersion at alpha, where these discrete residues are exactly the non-zero things that are left. So they have to be a zero precisely when F is rational summable. There is a Q version of the story. It's a little similar, but it gets a little bit more messy also. So now take a rational function F, and I'm going to be interested in the problem of whether I can write F as G of QX minus G of X. Okay, so it's a Q analog of F being somehow a derivative of G. And now I'm going to decompose F in a slightly different way. I'm going to first gather together the polynomial part of F together with all the poles just at zero. Okay, so I'm going to split apart the Laurent polynomial part of F. And then in the rest of the partial fraction decomposition, same sigma orbit, where now sigma is going to be the automorphism in that sense, x to q times x. And having done that decomposition, one then defines the discrete residues using a similar formula, but it now looks a little bit more complicated. Okay, so you're not just adding together all of the residues of order I at all the q to the n multiples of alpha, but now you're somehow twisting them by some power of q that involves both the order of the pole that you're at, as well as which shifted version of alpha you're on. Okay, so it's a little complicated, but in principle you can still compute it, so long as you know the partial fraction decomposition. More on that later. Another small complication in this q different situation is that now I also have to keep track of somehow a q residue at infinity, which is defined to be just the constant term of the Laurent polynomial part of the partial fraction decomposition of F. Okay, and Chin and Singer show once again that this collection of discrete residues at all of the sigma orbits of alpha for every pole alpha, together with this discrete residue at infinity, they form a perfect obstruction to the F being rational Q summable. That is, for F to look like some rational function G evaluated at Q times X minus G of X. Yeah, so F will look like that precisely when all the discrete residues at the finite poles and also this discrete residue at infinity vanish. And now I want to say a quick word about why care about residues. I've described so far as motivation 3 different kinds of residues, the classical ones that you know, and then the discrete residues in the shift case and the discrete residues in the Q difference case. One computational advantage that one somehow sees is that I can, if I don't care about what the G is that witnesses F being integrable or summable or Q summable, is that I can answer that question just yes or no without having to know what that G would look like. Okay, for me, these kinds of questions and more generally creative telescoping questions, which are some kind of souped-up version of asking for F to be summable or integrable, these questions arise in the context of a certain Galois theories for fields with operators, and very often one in practice you are interested in only answering yes or no is F of the special form without knowing what exactly the special form is. Okay, so the computation of the certificate in principle could be very expensive, and it's good to have a way of avoiding it. Now, the way that I've defined each kind of residue is not efficient, because it looks like in order to compute them, you would need to know what the partial fraction decomposition of F is, and that could very well be extremely expensive computation. There is hope, and I have open questions here that I'll get to in a second. In the differential case, I don't need to compute the full partial fraction decomposition of F if I'm only interested in knowing whether or not all the first order residues vanish. So in that case alone, there's this kind of trick. Okay, so there are some technical conditions I need to assume. F needs to be a reduced rational function, so take away the polynomial part, and then also let me suppose that the denominator is square free. The part of F that looks like this can be computed quite efficiently from the square free version of the partial fraction decomposition, which does not require expensive factorizations. Okay, so for a special F that looks like that, there's this so-called Rothstein-Traeger resultant. Okay, so it's a polynomial defined in terms of you know, the numerator and denominator of B, and this is as expensive as computing a determinant. Okay, and this polynomial happens to have the property that its roots are exactly the first order residues of F. So if you only care to know whether all of these first order residues are zero, all you need to do is compute this polynomial and then see whether it looks like z to some power, so that all of its first order poles are zero. I would love so much to have a version of this in any of the difference cases, whether the shift or the Q difference or eventually Mahler. And I believe in my heart that something like this exists. I just don't know what it is. And if you want to think about it with me, please get in touch. Okay. From a theoretical point of view, residues are also very useful. Okay, so I just want to give you the smallest telescoping kind of problem where one can directly get a powerful result using residues. So suppose that I'm either in the shift case, which I'll denote by S whenever I need to refer to it, or in the Q difference case. Okay, sigma sending X to Q times X for Q, a reasonable thing. And then in this case, I'm going to consider like a sigma delta structure on the rational functions over C, where in this case I pick a delta that happens to commute with the operator sigma. Okay, this is just a technical thing that that one needs in order to get a Gala theory that works well. And say that I have Z1 through Zn live in some sigma delta extension of C of X. So I'm thinking of K as some kind of Picard-Vesio extension of C of X, but let's not get into what that is. Suppose that K is just some extension that contains some elements in there, and all I know about them is that they satisfy this kind of first order homogeneous sigma difference equation, okay, for some coefficients in the rational functions. And I would like to know whether these Z's are or are not differentially dependent over the field of rational functions. By that I mean, I would like to know whether there exists some differential polynomial relationship among the Z's with coefficients being rational functions in X. And using their differential Gala theory for difference equations in this paper in 08, Haruan and Singer show that in order for the Z's to be differentially dependent, it's necessary and sufficient for them to be for the coefficients of the difference equations that define the Z's to be related in a very, very special way. Okay, so precisely there has to exist a non-zero linear differential operator, which when evaluated at the logarithmic derivatives of the A's happens to be summable. both in the shift and in the Q difference case. Okay, this result is homogeneously true in both cases. And the way they obtain this result is by using their then newly developed differential Galois theory. It turns out that you can capture any possible differential dependencies among the Z's by some Galois group, which in this case happens to be a subgroup of n copies of the multiplicative group. Okay, and the possible subgroups that occur in there, they're differential algebraic groups, and the possible differential algebraic subgroups of n copies of GM, the multiplicative group, were classified by Cassidy, and they're given precisely by such linear differential operators. Okay, so this kind of follows quite directly from having a reasonable Galois theory together with knowing what kinds of what the possible groups look like. So it turns out that if you also have available the technology of discrete residues invented by Chen and Singer, you can push this much further. I want to make really clear that the conclusion that we get, we don't have an independent approach to proving this fact, but rather we just build upon what Harduan and Singer already did. So taking their result as a starting point, and then looking carefully at what the discrete residues of the delta of A over A for each one of the A's looks like, you can get a much more special relationship. In fact, if the equivalent conditions of the Harduan-Singer proposition hold, then there actually exists an extremely special telescoper where the derivatives don't appear at all and the coefficients are all integers. And this is hilarious because it's a much stronger conclusion, and you get it for free just from looking carefully at what the discrete residues of these logarithmic derivatives are together with what happens to the discrete residues when you start differentiating something. So this is why we were extremely interested in developing a similar piece of technology that would work in the Mahler case and allow for all these different kinds of applications. Okay, so let me tell you for a second precisely what we're talking about in the Mahler situation. So you take an integer p, at least 2. I want to really emphasize that the p in here is not necessarily a prime, which can be confusing, but it's just the symbol that's traditionally used. Okay, and the Mahler operator is going to act C-linearly on rational functions by sending x to the p. One problem is that the sigma is not surjective onto rational functions, so it's not an automorphism. Some people mind this very much. So a trick that's often used is to enlarge the base field to include all the fractional powers of x, and that way sigma acting on k in the way that you would expect does happen to be an automorphism. So I'm going to say that rational function f is rational Mahler summable if again it looks like sigma of g minus g, where sigma is now the Mahler operator and g lives in this monster field. Actually, one can show that if f is rational summable in this weak sense, then it's rational summable in the strong sense that one can then find a certificate in the rational functions. Okay, you don't need to worry about the fractional powers of x, at least for answering these kinds of questions. Okay, and there's a little Galois theoretic trick that can be used to take g that in principle does involve some fractional powers of x, and then from it get a g that only has powers of x itself. Okay, now in order to tell you in a bit more detail what these Mahler residues are, I'm going to further decompose the partial fraction decomposition of f into a few different pieces. You'll remember that we've done this thrice already in the continuous differential case. I had the polynomial part, and then the first order poles were the only ones that mattered. and then in the shift case, I have to gather together all of the shifts of alpha. In the Q different case, I have to gather together all the Q to the n powers of the poles alpha, and then separate the Laurent polynomial part. So something similar is about to happen here. It's just slightly more complicated. So given a rational function, I can break apart its partial fraction decomposition into these three pieces, where the f sub l, L for Laurent, is a Laurent polynomial part of f, gather the polynomial together with all the poles at 0 or different orders. And then I'm going to separate, for small technical reasons, all of the poles at non-torsion elements of C star, that is all the alphas that are not roots of unity, and then split apart into a third case, all of the poles at roots of unity. The reason why roots of unity end up playing a special and frankly annoying role is that they happen to be exactly the pre-periodic points for the p to the n power maps. This case can be handled with careful bookkeeping, but it's a little bit different from just alphas that are not roots of unity. Okay, and in this way, you decompose the rational functions as a C vector space into these three different pieces. And what you see is that staring at it and seeing what sigma does, sigma actually preserves this direct sum decomposition. And so the only way in which a rational function f can be Mahler summable is if each one of these three pieces is individually Mahler summable inside of that piece. Okay, and this simplifies life just a little bit. Okay, so I'll tell you in great detail what the Laurent polynomial contribution is going to be. I'll kind of tell you what happens with the alphas that are not roots of unity, and I'm not going to get into the roots of unity at all. Okay, so to tell you what these Mahler residues at infinity are, that's the ones that are coming from the Laurent polynomial part. First, let me denote by the script p, just a monoid of powers of p under multiplication, the non-negative powers of p. And then I'm going to look at how p acts on z just by multiplication. Okay, so that makes z into a p module. Mind you, p is not a group, it's only a monoid, so you have to be a little bit careful, but things work, at least in this example, in the way that you would expect. I don't have orbits now, but I do have trajectories. Okay, starting at n, I can look at all the p to the n, p to some power times n. The maximal trajectories for this action of p on z, that said, I'm going to denote by t sub n. T for trajectories, but here I'm only looking at the ones where p does not divide n, because otherwise n comes from an even smaller n by multiplication, right? Having made these definitions, the Mahler discrete residue of a Laurent polynomial R at infinity is defined to be, well, what you do is for each one of these maximal p trajectories, you add together all the coefficients of the powers of x, where the exponents belong to that Mahler trajectory. And this happens to be precisely a perfect obstruction to the rational summability problem for Laurent polynomials. Okay, it's a little bit annoying. This is a vector. It's no longer just a number. But if you think about it, already in the other cases, if you have multiple discrete residues, the obstruction to the summability problem is also a vector of them. Okay, so I've just gathered them here for simplicity, instead of trying to talk about the Mahler discrete residue of R at infinity of order, I don't know, some bracket of n or something. Anyway, don't worry too much about this being a vector. It's fine.
Carlos,
Yes.
would you say what the main result is?
I will
then switch to questions.
Yes. The main result is that we have created Mahler residues for rational functions, and I'm not ready to write it down because we have formulas that are correct, but they are not pretty. So I want to tell you a little bit about what goes into them. The main technical problem that we had to solve was somehow getting control over what the partial fraction decomposition of this kind of monster is. It's a technical dilemma that goes into the proof. factors.
There will be additional opportunities to discuss further details. We have a couple of breaks, 30-minute breaks
Okay,
today. So
I'll stop here then. Thank you.
Thank you. All right. So questions?
I don't have question.
Questions?
So I got interested in the question you posed at the beginning about finding something similar to this resultant formula, but we can discuss this later to understand better what you meant.
Okay, great. Thank you.
So if you replace the derivative with the difference, it doesn't work. It's false.
I don't know. I have thought about it a little bit, but really only a little bit. Part of the problem is that in the difference case, you don't care just about the poles, but rather like certain sums of like a subcollection of them. And you need to somehow design a polynomial whose roots are exactly these sums. And so something a little bit different needs to be done, but I don't know what it is, and it's driving me crazy.
All right. Other questions? Okay, so Carlos, thank you again.
Thank you very much.
Let's stop the recording.